We're in section 4 of chapter 11 of Barnett's college math book, and this section deals with the chain rule. It's one of the most important rules in differentiation, and you should really carefully read this section to make sure you understand everything that's going on in there. Our goal for this section, our goals are obvious. It will be to form the composition of two functions, apply the general power rule, which is actually really the chain rule, and apply the chain rule itself. So why don't we start with a definition, and we'll remind you what's a composite of functions. Well, a function m is a composite of functions f and g if it could be written as f of g of x. The domain of m is the set of all numbers x so that x is in the domain of g and g of x is in the domain of f. The way this works is you have an input x here that you input into the function g, and once you get the output g of x, that output actually becomes the input, right? This output here, g of x, becomes the input for the function f. That's why the domain of m, the composition, is the set of all numbers x so that x is in the domain of g and g of x, the output, is in the domain of f because that output becomes an input. That's the key to it. Now let's talk about the general power rule. We've already made extensive use of this power rule that you've seen, x raised to some power n, and we've seen that the derivative of that expression is n times x to the n minus 1 power. For example, if I want the derivative with respect to x of x cubed, I know that that's 3 times x to the power 3 minus 1, or 3x squared. Well, we want to be able to generalize this rule so that you could differentiate composite functions of the form u of x to the power of n, where u of x is a differentiable function. In other words, I want to be able to have some function u here, in terms of x, that's being put to a power. Think of it as something like x cubed plus 7x squared minus 5 to the second power, let's say. I want to be able to differentiate that without having to FOIL out this polynomial, without having to multiply it by itself twice, in other words, and then take the derivative. So, does the power rule, is it still valid if we replace x with this function, which we'll call u of x? That's what we want to find out. Well, why don't we do it through an example? Let u of x equal 2x squared, and let f of x be the function u of x cubed. Well, when you cube 2x squared, right, which is our u of x, then you end up with 8 times x to the 6th. Which of the following is the derivative of f prime? And notice they have those derivatives in terms of u. So if we actually wrote out every single one of the cases, substituting in u of x equals 2x squared, and u prime of x equals 4x, right? When we take the derivative, we get 4x. We notice the following. First of all, the derivative of f prime, the derivative of 8x to the 6th, is 48 times x to the 5th. That we know. We want to see which one of these three cases will match that answer. So, if we try 3 times u of x to the second power, we get 3 times 2x squared to the second power, or 12x to the 4th. That's not a match to 48x to the 5th, and that's why it's incorrect. If we try 3 times u prime of x squared, that also doesn't work because we get 48x squared. However, if we try 3 u to the x squared times u prime of x, we actually end up with the correct response, 48x to the 5th. This is an example of what we call the generalized power rule. So the generalized power rule tells you if u is a function of x, then the derivative with respect to x of this function, raised to a power of n, is simply n times that function raised to the power of n minus 1, the whole thing multiplied by the derivative of the function with respect to x. So as a quick example, consider taking the derivative with respect to x of x squared plus 3x plus 5, the quantity cubed. Well, treat this as your u of x, or simply u. Then, according to the generalized power rule that we just went over above, the derivative must be the power brought down and made a multiple, 3. You keep the base the same, just like before, u, and u is now a function of x. You subtract 1 from the power, just like before, and now you have to make sure you multiply by the derivative of your base with respect to x, the derivative of our function, u, with respect to x. Since u is x squared plus 3x plus 5 here, its derivative is 2x plus 3. That's how we obtain the 2x plus 3 in the answer. And that's the generalized power rule. Well, the generalized power rule that we just used to find derivatives of composite function of the form f of g of x, where f of u was u to the power of n, is a power function. But what if f is not a power function? It is a more general rule, the chain rule, that enables us to compute the derivatives of many composite functions of the form f of g of x. And what the chain rule says is that if y is a function of u, and u itself is a function of g of x, we define the composition function y to be f of u or f of g of x. Then the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x, provided those two derivatives exist. Again, make sure to read your textbook very carefully about the chain rule. They have some nice explanations here. But we're going to use the chain rule to generalize these derivative rules. So in general, as we saw already, the derivative of any function raised to the n power is n times the function raised to the n minus 1 power. Okay, we have a second one here. The derivative of natural log of f of x is 1 over f times f prime of x. If y is ln of u, then y prime is 1 over u du dx. The third one that we have is e to the power of f of x. So e raised to some function f of x. The derivative of that is e to the f of x times f prime of x. Let's put those to action and look at some examples. Remember, in the following examples, this du dx term of the chain rule, these are marked by squares. You'll see squares around them. And the chain rule once again tells you the derivative of u raised to the power of n with respect to x is n u to the n minus 1 du dx. So if y is x to the fifth, that's the old chain rule, very simple, it's just 5x to the fourth. According to the generalized power rule, if y is 2x, the quantity raised to the fifth power, then the derivative would be, well, take the power, bring it down, make it a multiple, keep the base the same, subtract 1 from the power, and now don't forget to multiply by the derivative of the base. That's the 2, the derivative of 2x. That's how we get 160x to the fourth. How about this one? 2x cubed to the fifth power. Bring the power down, make it a multiple, keep the base the same, subtract 1 from the power. That's how we end up with that fourth here. And then take the derivative of the base with respect to x. The derivative of 2x cubed is 6x squared. That's how we end up with this answer. Here's another example of this. The derivative of 2x plus 1 is 2. That's being multiplied by 5, 2x plus 1 to the fourth power. Okay. Finally, here's an example with e to the x. We have e to the x, the whole thing raised to the fifth power. Well, this is still a function raised to a power. So the derivative is 5 e to the x to the fourth power times the derivative of e to the x. That's just e to the x. Remember, the derivative with respect to x of e to the x is just e to the x. That's how we get 5e to the 5x power. And finally, if we have ln of x as a function as our u raised to the fifth power, the derivative of that is 5 ln of x to the fourth power times the derivative of ln of x, which is 1 over x, as you remember from earlier. That's how we get that answer. Here's those more examples actually on this slide for exponential derivatives. So if we have y equals e to the 3x, then y prime would be e to the 3x times the derivative of my u, right? This is the formula we're following here. The derivative with respect to x of e to the u, where u is a function of x, that's just e to the u times du dx. So if the function is e to the 3x, I rewrite e to the 3x and I multiply by the derivative of u, which is 3x, with respect to x. That's how I get 3 to the 3x. If I have e to the 3x plus 1, the derivative of that is going to be itself times the derivative of the power, 3x plus 1 prime. That means derivative. So that's going to be e to the 3x plus 1 times 3, or 3 e to the 3x plus 1. And that's indeed the answer. Here's something a little more complicated. It's a trinomial here, e to the 4x squared minus 3x plus 5. Well, it's e to that power times the derivative of that power. You get the point. And finally, some examples for the logarithmic derivatives. If we have d dx of ln of u, where u is a function of x, the answer is always 1 over u times du dx. So if this is my u of x in this case, then the derivative is 1 over u right? This is u times the derivative of u with respect to x. This is the du dx, the 4. Let's do this one. Y equals ln of 4x plus 1. This is my u. So the derivative here is 1 over u times du dx, and the derivative of u is 4. So this is 4 over 4x plus 1, which is indeed the answer. You should double check your work for the remaining two problems here as well to make sure you understand this section. And again, for the third time, definitely read the chain rule section in the textbook.